Hi, hello everybody. This is Tom Sherrington, and I'm really glad to be taking part in the Chat Physics home learning version of the conference I know we were going to have. I was looking forward to that, but because we're all at home in lockdown, we can't get together. But here's a short version of the contribution that I was going to make, and it's fantastic to have something specific about physics. It's something I'm always very proud to say, that I'm a physics teacher, and that's how I started my career back in 1987. I had my first teaching job. I taught A-level physics for 3 years in a sixth form college in Wigan, and that's really where I cut my teeth learning how to teach properly from a subject specific point of view anyway. And I wanted to just in this talk about schema building in physics, linking the thinking about cognitive science into something which as physics teachers who might relate to more closely, and with a couple of examples. So in the time that we have, that's what I'm going to do. I hope that all the technology works okay. This is a diagram I use quite regularly in all the training that I do, because I think when we talk about learning, it can become a bit of a nebulous idea. What do we mean? So it's good to explore what we think is going on, and then relate to that model and pick it apart. Essentially, what we're doing is we're trying to form a model of the world in our head, so that which we can use and use to understand what we see and explore concepts in an abstract way, as well as relating to the physical world. And so we need to pay attention to what's going on. We need to focus on certain things. In our working memory, we can we absorb information in small steps, because we only can take in so much at a time. And then we connect it to what we already know. So what do we already know? And then how does this new information link to that? We actually kind of actively need to connect that. And then as we're remembering something, like it could be giving an explanation, or just thinking about why does that process happen? Why does that phenomenon happen? We're bringing stuff from our long-term memory into our working memory in order to kind of make it conscious to us, and thinking about that. And then we, again, engaging with the environment. And it's a cycle that goes round. The more regularly we review things, and the more accurate our recall is of the ideas we already have, then the stronger that memory becomes. But this idea of a schema is key, and it can be faulty. I mean, we can have a faulty schema, which is still how we think the world works, and there are plenty of examples of that in physics. So we need to be always evaluating the accuracy of our model in terms of new information, and that's obviously what a lot of science is about. Is do we understand things well? Can we verify that in the real world? And then do we have to change our model in order to then match the model to what we see, and that's how understanding develops. So I think thinking through a model like this is really useful in terms of understanding science and how science works, as well as just understanding memory. But the tricky thing with kids is that their version of the world is unseen to us. We can't see what they think. We have to try to draw out evidence about their model, which means that in teaching has to have this instructional, this interactive element. Like, what do you think this means? What do you think this does? Can you explain this? Can you predict that? And that type of thing. So I'm not going to go on too much about that in this talk, but I do think it's worth looking at in that scheme. I think this is a diagram I use a lot, this little animation, this idea that knowledge builds on knowledge. So you have a set of ideas, so new ideas come in, and then it has to connect, has to stick. And has to stick not just for the sense of remembering it later, but because the whole becomes your schema. So we've got new information, our schema develops, we enrich our view of the world as we get more information. And if it doesn't all connect and make sense, we can start getting misconceptions coming in later, or we start getting a slightly partial view of how things happen, and we can't make accurate predictions. And our sense of what we mean by understanding becomes distorted. So the way that knowledge accumulates and adds to existing knowledge is something we have to be thinking about, and be quite deliberate about that. So when you're teaching students, it's as important to work out what they already know and understand as to kind of give them new information. Because if what they already know and understand is partial, the stuff you expect to be there isn't there, you can waste a lot of time teaching the new stuff, which has no hope of making any sense to them, because what you were building on was poor. So sometimes the big task is, what do you already know about this? And then if you find there's horrible gaps, well, that's it. That's the curriculum plan aside. Let's go back to that, because let's just make sure that we get this, and this. And sometimes it could be as simple as like a term, a word, a phrase, a concept that has a meaning. And getting the students to agree the meaning of words so that we can apply them to a practical situation or something. And if you're assuming everyone knows what you mean by diffusion, say, and they really don't, then every time they're hearing it, they're just hearing you say blah blah blah, and you're assuming that means they'll make various conclusions from that, and actually they won't be. So you need to make sure you really understand what that word means and what it means in a real world way, not just a kind of definition off the top of my head kind of way. I also think this is important. So when we're building a schema, there are lots of different visualizations of this. People talk about there are lots of different metaphors that are used, but this is just one I picked for today's session. This idea that there are sometimes knowledge has specific elements, like very definable, which are things like a definition of a fact, a word, something you can measure, and something which you can then define, measure, be precise about, and check everyone has it. Because do you know this exact thing is something you can check for, and that's that grid, that kind of more rigid kind of set of things. But then the cloud represents a sort of this other set of knowledge, which is more like a sort of general sense of things, which you can't even really communicate to people. So how things feel. So if I'm thinking about, say, some magnets and how magnets repel, whenever I think of repulsion, I have this sort of recall, this sort of physical feeling I can visualize and remember, like the feeling of repulsion. It's a real thing, and how it gets stronger the closer the magnets are together. I can tell someone that. I can test them on their definition of repulsion, but I can't give them the feeling of repulsion. They have to get that for themselves. And that's true of lots of other things. This sense of, if you watch a fire, if you ever watch the flames in a fire, and looking at and trying to get the sense of the light emitting because of some sort of process that's going on, which is quite intense, and that sense of light being emitted by hot atoms essentially is something you can kind of talk about theoretically, but when you look and study it, that feeling of looking into fire and seeing light being emitted is a sense you kind of need to give people, and that's knowledge which has to be gained by looking in the real world experience, not by just being told things. So the type of knowledge which we need to make full sense of something, we need to have a broad understanding of. The terminal, this is a sort of A-level example. I like to include this because apart from anything else, having, now I'm not even working in a school all the time. This is a way of me kind of reminiscing about being a physics teacher. This is my favorite bit of board work, which I've done many times, but I remember taking a photograph of this. My handwriting's shocking, but the derivation of the ideal gas equation from first principles is one of my, I love the purity of it. And the fact that if you look on the, the right there, it links to the kind of the apparatus there. You've got a kind of a metal, a sphere here, and you can't really see the gas inside, but we're using sensors, and we're varying the pressure and temperature and so on. Well, mainly the temperature in that situation to see if the gas laws are obeyed, and it works pretty well. But I love the fact that you can derive an equation which actually shows itself in the real world by just talking about first principles. For me, it's one of my favorite bit of physics. So how do we get to that? This idea of a kind of a abstract knowledge, a visualization. You start by explaining this by trying to visual particles in a box and imagining them having an impact on a wall. So in order to be able to do that, the students need to be able to get into that space and thinking of impacts creating force and therefore pressure. And that's obviously in an A-level class. So by the time they get there, they will have developed that idea, and you can start talking about this imaginary particle going in a certain dimension and so on. But imagine what it's like to build that schema. How do we get to the point where you can have a good discussion with an A-level student about a physical piece of apparatus and then the kind of the theoretical explanation of it? Well, you need to start somewhere. This is one of my favorite things. This is my son's first science homework when he was at secondary school, and you can see it on the screen there. His first science lesson at secondary school, his teacher taught them about Democritus, the philosopher, and how Democritus had played with sand and water and observed that they had similar properties, that water could pour. I've got some water here, that water can change its shape and pour, and so can sand. And so sand is made of particles and behaves in a bit like water. So maybe water is also made of particles. And it's a visualization. So Democritus imagine water to be made of particles, and he called them atoma. And my son thought this was really cool, that a man could invent the concept of atoms just by thinking. And his first homework question, look at that, his first ever homework question was, what's the difference between science and philosophy? I thought that was fantastic. But the main thing in there is this idea, this visualization going on. Visualization, can you imagine? And getting everyone to think, what's it like in water? So you're starting to imagine particles. And this is exactly what, Democritus did a couple of thousand years ago. So we're building this idea of linking the macro world that we see with some subatomic world. And this is needs experience. You can't just tell people about this. You need to make that real for them. And we need to have a language. So we need to start talking about particles, energy, and it's links to some work people might have done about fundamental ideas in science. This comes from a school which was there. The main ideas that we talk about throughout the whole of science at Key Stage 3, particles, energy. So in talking about ice, water, and steam, particles, energy, physical change and not chemical change, and also scale, how many atoms are we talking about, rate of change in terms of how fast things happen. Most of the ideas in there, except that one biology example, relate to this exact thing. So some fundamental ideas, so you think, well, how do they apply? Well, we've got some language and some concepts. So going back to this, one of the things I think I often do at Key Stage 3 science is or even Key Stage 2 really, is getting kids to do things for real, like having their own block of ice, and seeing that it melts suddenly much more quickly in their hand because there's a source of energy there. And when a kid has got their own block of ice, it suddenly becomes like a special block of ice. Like, wow, it's mine. And they get more, they're observing, they're now scientifically observing a process rather than it just being, oh, ice. It's now my ice, this ice. And it becomes a sort of, you can get, awe and wonder out of that in plenty, because look, it's amazing. The atoms are moving, they're changing, they're separating. And that's interesting. And that it takes on new kind of meaning for them. And why? Now we have a question. Why is that happening? We have questions we can ask about something we have just observed with our own eyes. We can talk about other things like this glass of water. Actually, in preparing this video, I had ice floating here. I could put some in. There's the phenomenon of floating, ice floating, which is interesting, isn't it? Observing that. And why does that float? What does floating do? So we can talk about density and link it to the model of the atoms. The main reason I want to show this is that when I put the ice in, you can't see it probably there, but there's condensation on the outside because this is cold water. And you can discuss with kids, like, where does that come from? Why is it wet? Why is it wet here? And they've seen that probably hundreds of times, but never really thought about it. And they think, what? You get kids going, whoa. And it's condensation. It's interesting. It's a physical change, which is kind of commonplace, but those atoms, where do they come from? And their realization that they must have been in the air, or you can just tell them that and then make them think about it. There's water in the air, moisture, and that condenses because it's cold. And we have got a change of state happening right there. So this is interesting to me. You can create all the changes of state in a cup of water with some ice. And that is important. So we've got real world things which we can ask questions about, and then we have to sort of try to explain them. And how do we explain them? Well, we've got our words, but then we've also got things like this. And one of my favorite things, I love the FET Colorado. I've got it here online, so hopefully this works when you see the recording. You start thinking, well, we can model behaviors, and you need to play around with this before as a teacher and know how it works and know what to do. So I like this one because you've got neon, argon, oxygen, but you also have water. So it has little water molecules, and we can cool it right down. And I like the fact that when it's cooling it down, it pushes up this ice thing. So it's like it's icing the water, and it actually does a pretty good job. You can see as it goes very cold of kind of making the gaps there, and then we heat it back up again. And of course we can, as we get to around 0, we start seeing kind of this change of state going on. And this is an important visualization. Link it to what you're seeing here. We're seeing, and you're making the direct connection. That's what's happening there in a macroscopic atomic world. A microscopic atomic world. Here's our macro version, and getting the kids trying to make that connection. Can you see the link? How small do you think that is? It's really hard to get a sense of scale, but almost humanly impossible, really, because there's so many. The numbers are out of control, aren't they? But it's that kind of sense of it's happening at a tiny, tiny level. And that schema building, seeing that happening, making the connection, playing around with the variables, making predictions, what would happen if this happened, what would happen if that happened, what would we expect to see when it's a gas, etc., etc. So using a visualization like that, some kind of animation tool, of course, depends on the level that you're teaching it at and how much. There's a lot of detail in here, which is totally unnecessary for Key Stage 2 or 3, but definitely up to GCSE and A-level, you can get a lot more out of this and the whole kinetic theory. So schema building has this aspect to it of models, physical real world models, experiential knowledge, terminology, and the kind of mental model, the spatial model. And then you've got this, when you do something like the knowledge organizer, well, that has, remember what that's doing. That's in reminding that we've talked about changes of state. We know some common language. It's a reminder of stuff we've already got a schema for. I've been pretty disheartened to be in some lessons where I've seen kids given the knowledge organizer for states of matter, like that's it, job's done, and where they have not seen any of this, like all of that we just talked about has not happened, and this is their kind of, it's just stuff to learn, and it's such a poor quality curriculum experience to just be told stuff. There are some quiz questions, and it's all on the assumption that, oh, this stuff is a bit too fussy, maybe they can't be bothered to get them out. But even, there's learning just in having a cup of water on your table with some ice. And if you can't even be bothered to do that, you probably shouldn't be a science teacher. But it's important. Now you can also do a demo version once, kids don't have to have their own all the time, but looking at the real world versus the abstraction of it and the reminder of it, getting that right is important. Of course, then we can do retrieval practice using things like this because we've already seen it, and we can do things like quizzing, checking for knowledge, getting kids to explain it to each other. Can I explain what's going on in these diagrams? Well, I've got the knowledge organizer, you don't. I'm going to quiz you, and then you can quiz me. And this is the prompt and the reminder. I keep saying that because it's so important to get that right. And then we can explain things like this. We can explain things like the water cycle, which is another, real world application of the change of state, and using the terms that we have learned from the change of state to explain another thing, making connections with another area of the curriculum. I think that's important. So taking a kind of lab model of, ice and water in a beaker to macro, global scale is an important thing. And then, of course, that's something which you may or may not think is in your curriculum because maybe geography does it, but then you need to know who does it. But that's important, and seeing the connections. They may have done this at Key Stage 2. They will have done. Kids will have studied the water cycle at Key Stage 2. So if you're teaching science in Key Stage 3, knowing that is important, and then you can draw on it in your teaching and revisiting words that they ought to have learned. So there are some other things though. So I've talked about ice, water, and steam. To make it just more general, things like common misconceptions about phases of the moon and how it works and seeing the moon. One of the things I think we need to do is, again, how do you make something like that real? Well, the truth is that there's numbers. There's a visual model, so we need to get the scale right and the perspective. What models do you use? That getting a diagram which shows the true orientation is spatial models, Earth to moon. That's a great photo diagram which gives you the scale of both the Earth and the moon and the distance between them. And not everybody has that. So when you're seeing the moon, that's why you see it the size that you do, because that's where it is. And because of the angle of the Earth in relation to the Earth, that line in relation to the sun, we see these things. But also those things are directly observable. You don't have to just look at a diagram of that. Whenever we're doing this in a lesson, we should be tracking that with the class. What does the moon look like now? And we can say, well, we can't see it because it's the day, but maybe tonight, everybody track the moon. Let's have a little chart on the wall in our class. What does the moon look like today? What does the moon look like tomorrow? What do we think it will look like the day after? Let's predict. Were we right? So you can make predictions about the behavior of the moon for real. You don't have to pretend. You can do it for real with your actual class. And then the students are making predictions like scientists, and they're forming a schema of the moon is really there for real. And why do I see it like I do? Because I've got a model for where it is in relation to the sun and the Earth, and that's something you can do. It becomes more concrete. That's a tangible thing. Here's one of my favorite things. Okay, one of my ultimate favorite thing to do in science is check this out. Here we go. The classic Westminster kit. I've got this video of it. I could do this all day. Just watching, making that motor. Now, there's so many things going on there. There's the whole thing of the fact it's so humble. There's a bit of plastic, former, a wire, basic wire just wrapped round with a bit of fiddling around to get the terminals right. Some magnets which are in repulsion mode and they're orientated perpendicular to that wire there. But the fact that the motor works at all, in fact, the fact that you have to fiddle first is great because you can't take it for granted. It's not like, oh yeah, just motors work. No, they don't just work. They actually, you need to get it right. You need to get this sense of this commutator thing going on. And when it works, the satisfaction of having got it work makes you realize that there's stuff going on there which needs to be right. And so I do think there's value in the fact that it's not immediately successful. And it's good to have some working handy if people are struggling. But making a motor is a great experience. And I often talk about this in my training, that there are kids who have not had that experience who are then required to do this. So we get into the Flemings left-hand rule, BAM. And you know, what does B mean? You know, B is a definition. Okay, so a kid might say it's the magnetic flux density, but what is that? And they don't have this sort of tacit knowledge. They don't have this experience of the magnets being in an attractive field, not in repulsion. I might have said that wrong earlier. They're attracting. That's the strength of the magnetic field. And look, it's the orientation is like this because it's in that direction across the motor, and I can see it there. And the current is perpendicular to that. And knowing what that all means, because you've done it, is so much richer and more likely to not just be remembered, but understood. So when you're teaching, you can plan your scheme of work so that we have experiences, we build them in lower down the school. So we've made motors and they were fun. And we can talk about rotational direction, clockwise, anti-clockwise, the strength of the field. How could we make it go faster? How could we make it go the other way? What would happen if I did this? What would happen if I did that? Brilliant. You could do it as a bit of a class experiment, a bit of a demo combined. Later on, we have to formalize that. And we've got a lot more understanding about force, about current, about magnetic field. It's a great synoptic kind of topic. And then you bring it all together because the students have got recall from their schema of their actual experience. So that to me is important to get that right. Going in cold on this because it's on the revision guide and you didn't have time to do it properly, but too bad. You just remember F equals Bill is again a poor curriculum experience, and some kids get that. So just to finish off then, this is what I'm thinking. This is what you need to be thinking about: schema building. What is the tacit, concrete knowledge you can provide them, which they need, which you can't just tell them? What is that? What language do you need? You know, what terminology should we all understand? If we're talking about force, if we're talking about condensation, do we know what it means? Can they connect that to their experience? What are the problems that come out? You know, what are the questions we're asking? So why is it even interesting? You know, why is a motor interesting? It's interesting because it just works at all. Is why? But is it wet out on the outside of the glass? That's something we can ask. So what are the things that are surprising or interesting and need to be explained? That's part of exploring a schema, because then you ask those questions. The mental model. So what are you thinking about in your head when you see something in the real world? How do you visualize what's going on? Spatial models, like the phases of the moon. Where is everything in relation to itself? And then the sort of schematic. So with a motor, you know, often you'd simplify it to this sort of the Flemings left-hand rule as a way of sort of orientating forces and so on. What models and things do you help us explain? And then the maths, of course, you know, the equation, the maths gives us, you know, the fact that these things are multiplicative is interesting in itself. But yeah, the math, if I double that, I should double this and so on. And so those are things. So those to me is a combination of things to think about. And you know, some of that might have implications for some of the topics that you teach and the way you introduce them. And always having the ambition that all the students will learn all of this stuff, and you are pitching these models. Checking for understanding at each point is key. You know, not every child will get that straight away, and you need to allow for that, but at least giving the opportunity to think it through, get everyone thinking how you're visualizing it, what models, and talk explicitly with them about those models. Is important. So I hope that's been interesting and useful. I've certainly enjoyed having this opportunity to talk about physics. And thanks again to Fabio for inviting me to take part in the Chat Physics video conference. Thank you.